This afternoon session. The first speaker is Arefeh Kavand from Erlangen.
Yes, thank you for the introduction. Hello, everyone. So today I'm going to talk about a Primal-Dual augmented Lagrangian method for the solution of convex semi-definite programming problem, which is a recent work that we've been working on jointly with my supervisor, Michael Stinger and Michael Kochver. First, I'm going to talk about a dual and primal convergence analysis of penalty, barrier, multiplier, augmented Lagrangian algorithm. That's from now on, I'm going to use this abbreviation form PDMAL for this method. Let's have a quick look at the convergence analysis that has been done already in literature for this method. Benton and Zibolewski could produce a dual theory with sublinearity condition for the penalty update, but the drawback is it's not suitable in a STP setting. Also, Mosheyev and Zibolewski in their STP paper, they could present a convergence theory, but it's not complete. And also it requires high computational cost of penalty function. Dolzhensky and Tebul in this paper could introduce an exponential barrier method and a global dual convergence, even for constant penalty parameters, but the choice of their barrier function is not that practical. Kochver and Stingel in this paper, they could present a primal analysis and a local convergence with linear rate for sufficiently a small penalty parameter, and they required very strong conditions like LICQ or strict complementarity slackness. In theory, all these approaches need to solve the primal subproblems exactly. So, here in this presentation, we suggest to use a hyperbolic penalty function, which was introduced in Kochver. Yeah. So,
what is non-convex STP?
I'm sorry?
What is non-convex STP?
So actually, I'm just working on convex STPs, but STP which is not. Oh, so you mean that it's not related? Yeah. Sorry, maybe it's. Okay. I should find this. Oh, maybe I was referring to nonlinear, but not canonical decided, but that's the point. So here in this presentation, we suggest to use a hyperbolic penalty function introduced in Kochver and Stinger, and we can provide a full primal and dual convergence analysis for this PVM augmented Lagrangian method with the choice based on differential conjugates. Also, this only needs only a milk condition on the penalty parameter update, as well as an essentially as well as a Slater's regularity condition. So, the primal STP problem that we are working with had this formula in this box here. We show it by this STP. So this is a minimization of a linear objective function with the linear matrix inequalities or LMIs. These AIs and capital C and B are our data, and these matrices are in the space of n times n symmetric matrices, and we have n variables. And the standard dual for our STP problem having this formula here, which X is our Lagrange multiplier. The family of hyperbolic scalar penalty functions that we are using in our approach, having this formula here, which P is a positive quantity and it's our penalty parameter. But as we are working with matrices, so we are defining a primary matrix function, noting by capital phi corresponding to this scalar penalty function. So for that we are using the eigenvalue decomposition of the data matrices in order to somehow access the eigenvalues to apply this penalty function to eigenvalues in order to penalize any invisible eigenvalues, which in our case is non-negative eigenvalues. And our hyperbolic primary matrix function having this explicit formula, as you can see here. Okay. So The augmented Lagrangian associated with our STP problem. And here is the formula for that. The first term is just our linear function, linear objective function plus the inner product of our Lagrange multiplier and the V-squared of our data element constraint. Now, finally, we are able to present the PDM augmented Lagrangian algorithm in every outer iteration that we denoted by K. First step, we compute the new primal variable y K plus 1 by finding the minimization of this unconstrained problem. In the second step, we update our multiplier by this formula here. And at the end, we update our penalty parameter to get the pk plus 1. I should just quickly mention that this formula is coming from this fact that in every Lagrangian framework, we want this new yk plus 1 to be also a stationary point for our stationary points for our standard Lagrangian when we insert the new multiplier. So if you just put it, you can easily derive this formula in step 2. Oh, sorry, just okay. So the Lagrange dual of our problem, of our STP problem, having this formula here, it's a maximization of a non-smooth concave function subject to x to be positive semidefinite. This J of x is just a minimization of our standard Lagrangian. Just for your information, our standard Lagrangian have this formula here, just the objective linear function, and this is the inner product of our data elements and Lagrange multiplier. I should mention, it's really worth mentioning, to say that this STP, Lagrange dual STP, is equivalent to our dual STP, because for any visible x, if it's not satisfying to our equality constraint, then we cannot get a cost function that is acceptable. And vice versa, if it's x is visible and it can satisfy this equality constraint, then we can get a physical construction for this formula. There are two basic assumptions on our Lagrange dual STP problem, which second one, I want to note on the second one, which is about Slater constraint qualification condition on our Lagrange dual STP. And later we will see why we need this assumption. So now we want to know how we can manage to solve this Lagrange dual STP problem that I just introduced in the previous slide. We are going to apply a proximal point algorithm for that. So the proximal point algorithm is having this iterative formula, as you can see in this box. It's a maximization of g of x and this term here. This term having a formula, it's pk, you know it, it's a penalty parameter times capital B, x, and xk, which is distance-like function. So in the following slides, I'm going to explain how we derive this distance-like function. So it is somehow giving us a distance between the current iteration and the Lagrange multiplier of us. And it's also so the derivation of this data that I will explain later is based on differential conjugates. And it can also establish a link to subproblems in primal PDM algorithm. Okay, as I said, we are going to use differential conjugate to derive our distance function. As it's introduced already in this paper by Zvolevsky and Mosheyev, it's a formula, it's a generous formula to get the conjugate penalty function. So it's just the supremum of the inner product of x and a minus this term here, which this term having this formula here. So it's having a scalar outcome. Inner product of our phase iteration of our multiplier and then the square of our multiplier. And by using the formula presented here, and also a very important relation that is between the conjugate function and our penalty function, we can derive an explicit formula for our matrix conjugate function written here. By having this matrix conjugate function, now we can derive the formula for our matrix distance function using this conjugate function. And you can see in formula 4 for any visible x and y. So the generalized formulation for our distance matrix function. Okay, now we are going to have a look at the properties of this matrix distance function that I just introduced in the previous slide. The first one saying that D is continuous function and is strictly convex for any positive definite y. The second one is just the usual distance property that it says that it's non-negative and there is 0 if x and y are equal. And the third one says that if y is a positive semi-definite and x is bounded, then our distance function will be bounded too. Just a brief sketch of proof. So we know that for the first item, for the first property, we know that the square root of the matrix is strictly convex, so the minus is strictly convex, and that's why multiplying, this is the term that we have in our distance function. Multiplying by a full rank positive definite matrix can hold the strict convexity. And for the second item, it's really easy to follow because it's a strictly convex function, so unique minimum can be attained in this point. And the third one is also easy to follow because this is this inequality coming from the fact that B is non-negative. This is fixed, this is bounded, the whole term is bounded, and that's why this is bounded as well. Okay. So now we are going to construct the solution for our dual products algorithm. So first of all, we are reviewing some lemmas in order to warm up ourselves to build such this solution. Lemma 1 is saying that this minus 8 in yk plus 1 is a member of the convex subdifferential of minus g. The reason that instead of g we are saying minus g because g, if you remember, was concave, but its subdifferential is defined for convex. So that's why I just use a minus for that and having this general definition here. And lemma 2 giving us explicit formula for ayk plus 1, which is, I didn't bring the proof here because it can be followed by the update formula for the multiplier. So let's recall again our assumptions are our dual products problem. By having these two assumptions in our mind, this lemma is saying that there exists a unique xy in the space of positive definite matrices that can be maximization of this, that is a maximization of this problem, and can satisfy that optimality condition, which just this formula, the first one is the subdifferential of this term, and the second one, as you can see here, is the derivative of our distance matrix with the fixed y with respect to x. This is actually our A matrix as well. It's having exactly the same formula of A that was mentioned here. Okay, so, and now finally we are ready to talk about this corollary because it's really interesting because it's somehow giving us a bridge between our primal PBM algorithm and this proximal point. So it says that the xk plus 1 that we were producing in the second step of our PBM algorithm is equivalent to the unique maximization that we got from the proximal points algorithm. And the proof is just by using this playing this for 2 formula. I'm going to the details of the proof. So now we are very close to the main theorem of the dual convergent analysis, but before let's have a look at this lemma. It says that we assume that xk is a sequence generated by the dual products algorithm. Gxk is non-decreasing. We can show that Gxk is non-decreasing, and we can also show this very important inequality. Why I'm saying this inequality is important? Because it's somehow giving us the information that how we can update our penalty parameter, as well as it's also telling us that what is the rate of our convergence. So again, I just put the sketch of the proof, which For the first one, it's just coming from the the non-negativity property of P, and that's if K is the maximizer. So of course, we have this inequality. And the second one also is really followed, just coming from the definition of the subdifferential inequality, convexity, and non-negativity of P, and we can easily get this inequality in the second item. Okay, so this is a theorem that's talking about convergence for the dual Crux algorithm. So let's assume that xk is again a sequence generated by a dual Crux algorithm. Xk is bounded, and if we let pk goes to 0, then we get the convergence in our function dual, the dual function values, which this JSR is just the maximization of our problem. So the detailed proof of all this lemma and theorem are on my backup slide. So if anyone is interested, please do not hesitate to ask. I can provide it. So as I promised, we are going to also talk about the primal convergence analysis as well. But this one is shorter. We just again assume two assumptions on our STP problem. The first one is saying that the set of optimal solutions for STP problem is non-empty and compact. The second one, again, the Slater condition also holds for the STP problem as well. Again, this is just the recall of our PBM augmented Lagrangian algorithm, as we remember, but with this difference that this time we know that this xk plus 1 produced in the second step is equivalent to the xk plus 1 we get from our Crux algorithm. Okay. So, the theorem is the theorem for the convergence of a primal STP. Let's assume that xk by k are generated by this algorithm, and these conditions, these assumptions hold. For k goes to infinity, we can show the asymptotic primal feasibility. We can show complementarity slackness. We can show the convergence of along the convergence of the function values. And at the end, xk by k are bounded. So we can also show that they are bounded, and each of their accumulation or the limit points is a pair of optimal solution to the dual and primal STP problems. So now I'm going to talk about a Primal-Dual augmented Lagrangian approach again. I'm using this abbreviation form of our approach, PDAF. So, but first of all, I'm somehow trying to make some motivation why we are using this new approach that I will explain in details. I just want to draw your attention. So, this is the minimization problem that it's in our subproblems. This is our augmented Lagrangian. So, if you remember, I told you in the first step of our PBM algorithm, they're computing this y plus 1. And this is our dual Crux algorithm that we could get this xk plus 1. But in order to get such this yk plus 1, it's this problem, this minimization and transfer problem should be fully solved, which in practice, we tried it, it's really expensive. I'm going to tell you the remedy for that, but before, let's have a look at this differential duality. So, again, this is from the previous slide, nothing new. This is the weak differential duality. It says that for any physical y and x, we can have such this inequality, or it says that f can be an upper bound for any dual maximization problem. This is just a weak duality, but in the differential calculus sense. The sketch of proof is just coming from the definition of our conjugate function, conjugate penalty function. And also, we are also having a strong differential duality. So imagine that this yk plus 1 is the minimization for this convex problem, and xk plus 1 is the maximization for that concave problem. Their function values coincide. This strong differential duality is the same. And again, the sketch of proof is just by using the update multiplier formula, multiplier update formula. So we assume that we only stop our algorithm as soon as we get an x hat k, which this x hat is fully dual feasible, it's like positive definite, and it can also satisfy this equality constraint. So if we have such this x hat k getting from the area stopping, so this is just a disciplinary inequality that's going to be used here when we go to the details of that, but it's just coming from the potential duality inequality that was just introduced. So we can get such this important quantity here, which is called the potential duality gap, which is a positive quantity. So for example, when we are doing the subproblems, we don't know if we are stopping, for example, in this x hat k, we don't know how far we are from the solution, but by having this quantity in hand, we also tried it in practice, implemented too. By having this in our mind in hand, so we could somehow have some information as well. That's really helpful, thanks to potential strong and weak duality. So this lemma, I'm not going to talk about it. I'm not going to focus on it that much because I just need this in an important inequality of this lemma, which is the maximal increase possible in the dual parts function. I need this inequality, the last inequality, in order to get this star condition. This star condition is helping us to prove somehow this one that I will explain it later. But okay, this delta k is just a fixed quantity greater than 1. In our implementation, we usually put 2 for that or something. And so the right hand side, this term goes to 0 because G star is finite. This term goes to 0 if pk goes to 0. The pk goes to 0. P is bounded, so the whole term goes to 0. That's why delta k goes to 0 for k goes to infinity. And that's why we can get the convergence if we are stopping also early with this x hat k. Okay. So now let's talk about this primal-dual augmented Lagrangian. Now we somehow motivated ourselves that we know that this x hat k, but the question is how we can find such this x hat k in order to be positive definite, satisfy this equality constraint, and also satisfy the star condition that I introduced in the previous slide. How we can get it? This is never happening if we use the primal sequence, if we use our primal PBM augmented Lagrangian algorithm that I explained earlier in my talk. So this is the motivation for us to do a split. But first of all, this is coming. We got the inspiration from the work by Greenbaum and Collier in this paper, this PDAL idea. So what we are doing is we split the Newton system that we had in our primal PDM algorithm to these two equations. So if we do so, due to the linearity structure of the first equation, it can be fully solved or satisfied. And then after finitely many iterations, they're all tested in our implementation. We could see that after finitely many iterations, this condition was satisfied, that we could get a strictly feasible multiplier. And then we could immediately stop when it was happening. Because before using this idea of PDAL, we were solving the problem by many inner iterations, like 300, without any improvement, and we didn't know how to stop. So by using this technique, immediately when we get such this strictly feasible multiplier, we immediately stop. And also we could see that along the iteration, this delta k that was our potential duality gap was also decreasing as well, going to the 0. So, okay, this is just our PDAL algorithm, and just with the, in every outer iteration, we initialize our multiplier and primal variable, and we enter the inner loop for solving the subproblem. And so whenever we complete the connection and real conversion, and whenever this dual feasibility is satisfied, we can update. And we can also optionally, that's why I call it hybrid, because we can also having this option to having this earlier studying with our primal multiplier update, the second step of our PDM algorithm. And then, yes, we update the inner iteration, primal and multiplier in the inner iteration, and at the end we update in the outer iteration, the multiplier as well as the penalty parameter. This is the whole PDAL algorithm that we are using. Okay, so I should also mention that the linear system in our PDAL algorithm can be either approached by direct solver or by the precondition conjugate gradient method. For this, we are using a preconditioner it should satisfy this assumption that X or a multiplier should be low rank. The proper preconditioner will be presented by the next step. I'm not going to go to the details because we also use the idea and we also could apply it successfully in our approach as well. So now we are there to present the numerical results. We are testing our approach PDAL in two class of problems. First of all, the study library by Porters. We are using direct solver for these problems and the Dymax error. The Dymax error of us is just the KKT condition, just for your information. And the purpose of doing this test is to compare three different strategies that we have. Like traditional, or I can say the primal PDM augmented Lagrangian algorithm, PDAL without primal updates, and PDAL with optional primal, that we call it hybrid in our algorithm. So these are the selected examples from this SPT library. So as you can see, this is the Primal-Dual and this is the hybrid. This green part is the number of iterations that you can see. It's quite less, not that much significant, but it's doing well. So on average, the PDAL yearly performs the purely primal strategy. And yes, this is selected examples. For example, here we are having 400 for the purely primal, but this is only 37. And as I said, we can also handle problems if we are having proper preconditioner in hand, which will be discussed in the next slide. For example, we could be also able to solve these cross and vibra problems. These two tables are the sizes of these problems. These problems are beyond the scope of SPT software if you want to use direct solver. And for this problem, the low rank assumption is satisfied, and that's why we can use our preconditioner for that. Yes, and here are the numerical results with two different Dymax precision, 10 to minus 5, 10 to minus 7, for the selected truss problems. Yeah. Again, the PDAL is doing better than the purely PDM augmented Lagrangian algorithm in the green areas. And also the same for the vibra problems with two different, again, Dymax precision. You see that it's even failed if you pursue the purely PDM augmented Lagrangian algorithm. So, and here these two are actually, as I said, this is the recent work that we've been working on, and now we are also recently working on do the same theorem for the iterative solver. Also, we want to do the implementation for the iterative solver as well. And the references. Thanks for your listening.
Are there any questions in the audience?
Sure.
Very nice.
So did you compare with a classical SDP solver like like Mosaic?
So actually,
How does this solver compare?
yeah, so we are having an archive paper with Birmingham. So in this, they are presenting some tables that they are having because they're working with interior point method. So they are using this, they are doing this comparison, and also they put our results there. So I can't say that we are also writing a paper for ourselves only for PDAL, but we are not doing any comparison to Mosaic or something. But I know that SDP9, we could do a comparison, but not for Mosaic actually, as far as I know.
Yeah.
Yeah, but because
it would be interesting, yes. How it would be interesting to know how they are.
Of course.
If they are faster, but maybe less precise, or you are doing better on the precision or the efficiency.
Maybe I could comment on that. So the first goal was to solve it for and problems always, so not to compete with Mosaic. But in general, so if you just look at standard SDPs, not with all solutions, this would be slower, but definitely more robust. Already the original Augmented Lagrangian code, and this is like an improvement of that. Already the original one was more robust in the sense that it can solve more problems to higher accuracy. And the promise is this should be even better.
Okay, any other questions?
Slide 19.
Oh, 19.
Accumulation 9.
Okay.
Yeah, point 4. They said that each accumulation point gives an optimal solution. Did you also see that it's often happened that there were many accumulation points?
Yes.
And did it mess somehow with the algorithm when it was choosing between several solutions?
That's no, actually, we didn't check that, but it was a we didn't come up to the problem for that. And I don't know how many of these accumulation points we have, but it wasn't a problem.
It can happen that there are several.
Sorry?
But it can happen that there are several different.
Yeah, exactly. Yes, it's not unique.
Other questions? I'll ask a question. So in the tables, you reported the number of iterations per method. How does the computation time per iteration compare?
So we are just maybe this is not a good one. Computation. I'm not talking about the CPU time. You mean this?
So I meant, so here you have the primal Newton, primal CQ, dual Newton, dual CQ, and all these different possibilities.
Yes.
And you report the number of iterations, but what is the time per iteration?
Yeah, it's not reported actually. Also, we didn't report it in our paper because for us, mostly it was important to see how many iterations we can get. But actually, it wasn't reported in my paper. That's why I didn't bring it here. But we just have these numbers for the very large and for the very large cases. Yeah. I don't have it in hand now.
Maybe the iterations are the same cost. No.
I actually don't know. I should have a look again in the paper about the CPU time. It's been a long time ago, but yeah, good point. Can refer to.
If not, then let's thank you again. We have an 11-minute break.